All right, it's time to go over the first assignment regarding continuity, which was the section 2.3 packet problems 1 through 18. The first 10 questions are really less about massive amounts of work and more about just reviewing discontinuities. Now, I will say a couple people commented, either they didn't understand the answers that were given in the back of the course pack, which started on page 339, maybe even 338. Some people understood the work, or at least the explanations, and just commented, uh, regarding whether or not they had to show that kind of work. And um, I don't think so. I mean, the directions just say find the points of discontinuity and identify the kind of discontinuity it is. So if you did that, you might have to show a little factoring on number 2, and that's really about it. Some of these you may have needed to graph because you didn't understand, the function as well as maybe, just a basic parent function. But that's really all you needed to do. So say, like on number 1, you could say there is a point of discontinuity to x equals -2. It creates a vertical asymptote, which is an infinite discontinuity. So, complete sentences are good. Detail, as far as, where is it? It's always, this points of discontinuity are always going to be x values. X equals this, x equals that. Now, I will explain what they did. Whoever typed these up, and these answers have been like this for a while, so I'm assuming it was probably Mr. Tritch, who hasn't even been around for probably 5 or 6 years now. But um, he was going back, I think, to the definition of continuous functions. This is something that was in the lecture, where if a function is continuous over an interval, that means that at any point, every single point in that interval, it must be continuous. But to be a continuous function, it just has to be continuous at every point in its domain. And so I think he was trying to explain why these functions, despite the fact that some of them had discontinuities, were continuous functions. And so if it was confusing, I think it's because more information was being given than was being requested. Somebody made the comment like, I don't understand the work that there is, and there isn't any work really. It's just explanation. So it's more using a definition, and then information about the function in conjunction with the definition rather than showing any work. Now, like I said on number 1, the only value that will create a 0 in the denominator is -2. We know that when we divide a constant like 1 by 0, we get an undefined value that is, it's basically trying to achieve infinity, right? Because 0 fits into 1 infinitely many times, although it will never fill it. So we're going to get an infinite discontinuity because of the vertical asymptote. The one thing I would have liked is if these were in complete sentences a little bit more. Something that would have been on your next quiz had we taken it under normal conditions would have been a couple questions that ask you to break down a function. Here's a function. Tell us about the points of discontinuity, describe what they are. And it says, use complete sentences when you do this. A lot of students just don't. So when you are doing these written feedback questions, you should do that, although you weren't asked to do that on this, to this degree. Number 2, if you factor the denominator here, you get x minus 3, x minus 1. Neither one of those cancel with the top, so there's no holes. These are both going to be vertical asymptotes, which create infinite discontinuities, and that's of course what we ended up saying right here. Okay. 1 over x squared plus 1 on the next one. that is never going to achieve a zero. I mean, at first you're like, well, what x could I put in to achieve a zero? I guess you could put in an I, right? But because it's a parabola, which only has a single point of on the x-axis at zero, and then it gets shifted up one. Um, there are no values which we can get a zero in the bottom. So this is going to be no discontinuities and continuous overall real numbers. Um, let's see here. Number 4 is just an absolute value function. We know absolute value functions normally are right here at the 0, 0, but this one got, it looks like, translated 1 unit to the right. That's what that x minus 1 is going to do for us. And so there are no points of discontinuity for absolute value functions. There are no breaks in the graph. Of course, it doesn't look like that because I used a dotted line for some crazy reason. So I'll, boom, now it's not dotted anymore. Cool. Yeah, here's an explanation that's trying to explain why it's continuous using the properties of continuous functions we talked about. Remember in the notes from yesterday, part of the lecture, and then you could also find it on page, I believe, 315. It says that if you have two continuous functions and you add them, subtract them, multiply them, divide them, or even take compositions of them, they will continue to generate continuous functions. And that's what they're saying here, is if the absolute value of x is continuous and x minus 1, which is just a line, is continuous, then f of g of x, putting the line into the absolute value, is continuous, and that's what we see here. Number 4, by the way, no points of discontinuity on number 4, right? That's really what we were trying to answer. Number 5 is a square root function, so we know it's not going to be defined everywhere, but there are no points of discontinuity. I mean, it doesn't go past its beginning point, which, by the way, normally is at 0, 0, but it looks like this guy has been, look at the work up here, right? That's how we did it back in Unit 1, was shifted or translated to the left about 1.5 points, right? So that's what that looks like. So it's not defined anywhere over here. But remember, continuous functions just have to be continuous over their entire domain. And just solve for the domain of this function, and it is continuous everywhere from that point on. This is a continuous function. There are no points of discontinuity, even though it's not defined to the left of negative 1.5. Number 6 is an odd root. And we know that odd roots don't have the issue with creating negative radicans, so they go back and forth forever. So it's continuous over all real numbers and has no points of discontinuity. Once again, there's an argument on both of these where we're saying, hey, I could make this a composition of two continuous functions, and so that's one way of kind of proving that they have to be continuous, is by breaking them into simpler functions, which we know are continuous by nature. That takes us to number 7, where things finally start to get a little interesting. Although this is a function, I must say, that we have seen already a couple times. It's almost a number divided by itself, which would just be 1 forever, right? 5 divided by 5, 10 divided by 10, 50 divided by 50 would always be 1, except that instead of just x over x, we take the absolute value of one of those x's. Well, what that's going to do to the left of the y-axis is leave the numerator positive while the denominator turns negative, and we get negative 1. What that does here is create a jump discontinuity. And so there is a jump discontinuity at x equals 0. However, 0 is not part of the domain of this function because it creates an undefined value. And so we could still make the argument that this is a continuous function. And the way they did it is they said, hey, absolute value of x is continuous, x is continuous, and when I divide two continuous functions, as long as the denominator is not 0, which is why we took this out, right, you get a continuous function. Number 8, they just broke cotangent into cosine over sine. And cosine is continuous, sine is continuous, so the division would have to be continuous. However, sine is 0 at infinitely many different values. Sine is 0 at 0 pi, 2 pi, 3 pi, and so on. So at integer multiples of pi. So we know that there will be infinite discontinuities, right, created by those vertical asymptotes at all integer multiples of pi. I don't know why that's not typed here, but it's not. However, it might be in your course pack. Nope, they did not write it. So that was omitted for some reason. That's really the important part of this problem is where is it discontinuous and at what point. So I will tell you right now that the answer for this in a nice complete sentence, number 8 here should have been y is discontinuous at all integer multiples of pi. Those discontinuities will be infinite discontinuities created by vertical asymptotes. So there's what should have been left there as far as the answer to the actual question. Number 9 is probably, to me, the most challenging of this bunch. 1 over x is a fraction which is going to get really, really tiny as we go towards the ends of a graph, and really, really huge as we get near 0, right? Well, what that means is we're going to be taking e to the almost 0 the further out we go, and anything to the 0 is 1. So we're going to have a horizontal asymptote approaching 1. But as far as discontinuities, I think we need to look about closer to 0, because when I plug a 0 into 1 over x, I get an undefined value, right? You can't plug a 0. And sure enough, we see as we come toward the y-axis here that I have a vertical asymptote at 0, but it doesn't seem like I have one coming from the left, only from the right. That is interesting. Well, if we think about what's happening, if we come from the right, you have negative values. And so you're taking e to sometimes negative roots, sometimes, negative odd roots. I mean, it doesn't seem like it makes sense. So what I did is I created a table. And we can see as we come in from the right, like I'm really, really close to the right, 2.7 times 10 to the 43rd is a fantastically huge number, isn't it? I mean, that's a 2 and, then a 6 and an 8 and 8, and then like 40 more zeros after that. That's massive. On the other hand, as I come in from the left, I get the same distance away. I get 3.72 and then to the negative 44th. So that means I need 43 more zeros before that 3. That's a ridiculously tiny number. So huge numbers from the right, tiny numbers from the left. Now, even though it is getting really close to 0, I can't put 0 into this function. And so we are never going to actually achieve the value of 0. But because of the vertical asymptote, I do have the infinite discontinuity created coming especially in from the right. And then the last one is just a log function that's been shifted 1 unit to the left. We know that logs are continuous functions. They're just not defined everywhere. So this log over its entire domain is indeed continuous. So there are no points of discontinuity for this function, even though it's not defined anywhere to the left or at -1. So I hope that explains it. This is way more information than you really probably needed to get into as far as explaining the rules of why the functions are continuous or how they could be broken into compositions. You really just needed to give what types of discontinuities there were. And you only have certain types, right? You have the pointwise or removable discontinuity created by holes, the infinite discontinuity created by vertical asymptotes, the jump discontinuity, which usually happens in piecewise functions, but we do see it in the greatest integer function. And then, of course, the oscillating discontinuity, which you're really not going to see. Just to make it clear from yesterday, the dactylian discontinuity named after the pterodactyl is not real. I just don't want anybody to write about that at some point on a future assessment because, yeah, that was not true, as it turned out. All right. There were a number of questions on 11 through 18, so let me get to those. I'm assuming you've already checked these answers. They are all in the back of the course pack on page like 39 and 40, right? If not, then go ahead and pause the video and check them, and then we're going to talk about them. Specifically, we're going to talk about problem 13 first. Looks like nobody had questions on 11 or 12, but on number 13, is f defined at 2? So that just wants to know if the function has a value at 2. So we look over here at 2. Let's make a little strip right around 2, right? And I don't see any points where it would have a value. Like it's definitely not defined at the hole here, but it's not like they define it anywhere else. So I got 1, right? There's a hole, but then they define the function at another point. So it's not defined at 2. So my answer for 13a would be no. And because there's a hole at the point 2, 0, it's definitely not continuous at 2. I mean, if they really asked you to explain this right here, if they really wanted you to give a written explanation, then you would need to go and take your definition of continuity, which is what we learned yesterday. This is that definition that says the limit has to exist and be equal to the function's value at that limit. Okay, the function's value has to be equal to the limit's value. So half of that condition actually is met here. Okay, at 2. So let me show you how we would kind of write that out. We would say, the limit. Well, we don't really want to do that. The limit for f of x sx approaches 2 is equal to 0. Okay, because the left limit as we approach is approaching a height of 0, right? And the right limit as we approach 2 is approaching a height of 0. So we definitely have a limit. But f of 2, so do you see how the c value that we were using here, 2, ends up going into the function, is undefined. They didn't give us a value for this function at 2. And so that it cannot be continuous at 2. All right, so that's how you would handle number 13 using that definition of continuity. The next question was 14. And at what values is f continuous? So even though there aren't very many chunks of this graph, just a little piece here, a little piece here, a little piece here, because of the density of the real numbers, there are infinitely many points where this function is continuous. So I do not think we want to answer this question in the affirmative way. Okay. I think what we want to do is we want to talk about where it's, or at least locate where it's not continuous, and then just say it's continuous everywhere else. So here's how I think we could do that. Start at the left, because we're only defined from -1 to 3 is kind of where this function exists, right? -1 is where it starts. 3, not including 3, is where it ends. So let's start at -1 and just kind of trace our way along and see where the discontinuities occur. The first discontinuity is a jump discontinuity at x equals 0. The second discontinuity is a removable discontinuity at x equals 1. And then another removable discontinuity at x equals 2. And then finally a final removable discontinuity at x equals 3. So I would say that this function is continuous everywhere from -1 up to but not including 3, except for at x equals 0, x equals 1, and x equals 2. And because we didn't include 3 in the interval, we wouldn't have to include that. So here's some ways that we can do that. This is probably the way we should be most formally used to right now. We took that interval, -1 to 3, and what I basically did is I plucked out all the bad values, right? I took out 0 for the jump discontinuity. I took out 1 and 2 for the holes, and then we weren't including 3 to begin with. And so I think that's the way that I would answer. If I was you, I would answer number 14. I would say not necessarily where is it, at what points is it continuous. I would say where is it not, and then remove those, and everything else is good. Okay. Now here's another way you could kind of do it. You could say, hey, everything from -1 to 3 except these 4 points. But this is not really an except in a form as the interval notation that we've been using so much this semester. The next question was number 16, which is actually very similar to number 15. Number 15 is what value should be assigned to f of 2 to make this a continuous function. So if we look down at 2, you see there's a problem. There's a removable discontinuity there, isn't it? So the reason is, the limit exists. The limit is 0. And I think we talked about this on the previous page. The left limit approaches 0, the right limit approaches 0, height of 0, right? X approaches 2. But there's a hole there, so there's a removable discontinuity. So what can I do with this function to fix that? Well, the easiest thing to do is probably to say, somewhere in here that that x or f of x, I should say, right? F of x is equal to 0 at x equals 2. So when x is equal to 2, kind of like up here they said when x is equal to 1, f of x is 1. I would say when x is equal to 2, but f of x is 0. And what that would do is that would plug the hole. Now, another way I guess you could take care of that is to create a situation where, this is included or this is included, and then you would plug that hole by adding that. But that would be more changing the function, so I think you're better off plugging the hole independently. So the question that was actually asked, number 16, is almost the same, except it's asking about what's happening at 1. Okay. Now I have the same issue. I have f of 1 equal to a value, though this time, whereas at 2 there was no value assigned at all. So it tells me here that f of 1 has to be equal to 1. The problem is that the left and right limit as we approach, as x approaches 1, is equal to a height of 2, right? And so that's what creates a removable discontinuity, is when the limit exists, but the function's value is not equal to the limit at that point. It's so important to understand this definition from yesterday. That's what this is saying, right? This is saying that the function's limit has to be equal to the limit for each point you approach to maintain, to get that continuity that we want. This one's a little easier to fix though, because it does already have a defined value for the function at 1. It's just the wrong value. So why don't we go back into the function and redefine the value of the function at 2 when x equals 1. And that would take this point and it would move it up here and plug that hole, and suddenly I have continuity. That makes everybody much happier, right? So that's how I would do number 16 for whoever asked that one. Hopefully that makes sense. We just fix the function to control that, plug that removable discontinuity. Now number 17 asks if it's possible to extend f to be continuous at x equals 0. Totally different case, because these were removable discontinuities, which meant we could fix them. They could be removed because it's easy to just redefine a function to fill a hole. And this is precisely what you guys are going to be learning tomorrow or today, I guess, looking at the time. In the second lesson on 2.3, we really have one big thing that we add, and that's the how to write an extended function to fix a hole. So here we're talking about where we can do it and where we can't. Tomorrow we really learn how to write the full function out, which is something we didn't quite have to do on this set of problems. At 0, there's a totally different problem, guys. This is a jump discontinuity, okay? And so we have an issue where the left limit, so the limit of f of x as x approaches 0 from the left is equal to -1, right? We're driving down towards a height of -1. The right limit as x approaches 0, so now we're approaching 0 from the right of f of x, on the other hand, is equal to 0, right? Here we're coming into a height of 0. And that creates exactly what you see, a big old gap. And so I can't fix one thing, and it's not like by plugging in, this hole right here, it's going to fix anything. It's still there. That's why jump discontinuities and infinite discontinuities, and oscillating discontinuities, although we don't really deal with those, that's why they're not called removable. Only holes create removable discontinuities. They're the only ones we can fix. So, as far as number 17 goes, is it possible to extend f? So that means like fix it to be continuous at x equals 0? And the answer is no. So, if so, what value should be extended? But there isn't one, and why not? What I wrote for you is kind of the answer. The limit doesn't exist at 0 because the left limit and the right limit don't equal each other. And remember, there's 2 conditions for continuity. First of all, the limit has to exist, meaning the 2 one-sided limits have to agree, and that did not happen here. And if that doesn't happen, you don't even have to do the second check, which is where you assure that the function's value at that point is equal to the limit to plug any possible hole. So hopefully whoever asked number 17, that explains that it's really the difference between, fixing this, which we can't do, fixing these dudes, which we can do, and in fact, even this one we can fix. We can fix 3, and that's what number 18 is asking about. Is it possible to extend the function to be continuous at x equals 3? Sure. The only difference about that one compared to the other ones is the first 3 points, 0, 1, and 2, were all interior points. 3 is an endpoint for this interval. So we can only, in this case, talk about the left limit. We cannot talk about anything else. So the limit, though, is definitely it's at 0 the whole way through, and it's approaching a height of 0. That's not changing. So we can definitely talk about the one-sided limit being, sorry, I don't know why I wrote 1, 0, true. Okay. But when we get to 0, there's a hole there, so that breaks the continuity. Step 1 worked. The one-sided limit existed. Step 2 did not. The function is not defined at x equals 3. There's no point anywhere along this area, is there? There's no point for x equals 3. So how do we fix that? Well, the easiest way would just be to come over here and say, well, we're already equal to 0 coming in from 2. Why don't we just make it equal to 3? And now we have it fixed. But normally you're supposed to not add it on to symbols that are already there. So I think what you probably want to do is say, oh, by the way, if x is equal to 3, then the value is 0, and that would plug that hole in and make it continuous at the end of the interval. And so that's the way to extend the function. So could we fix it? Yes. Is it possible? Yes. And what should the value of the extended function be there? Well, it should be 0 when the height is 0, and that's why it can be fixed. So hopefully the problems that you were going over, or the answers that you were reading over, kind of eliminated that. Let's see here. So number 17 was no, the right-hand limit and left-hand limits are not the same. They probably should have finished that off by saying, so the limit does not exist at x equals 0, which prevents continuity from occurring. That would have been a slightly better answer. Number 18, yes, it is possible to extend the function. We just need to have the function's value at 3 be equal to 0. And so pretty much exactly what we talked about. So hopefully those explanations help. Wrapping your mind around this definition is really the key this week, understanding what this means. And we'll talk next about fixing removable discontinuities. How do we rewrite equations for that to happen? See you then.